So, of course, there's no class on Monday, okay, so don't come on Monday. However, remember that our assignments are still due on Monday at the normal time at 10:30. All right, so if you don't want to do it on Monday for the holiday, you want to take the holiday off, then do it before then. All right, our next SI is on Tuesday. We have everything, all these things going on. Remember, our next exam coming up is a week from Monday. All right, so today we will be finishing Chapter 18. Next week, hopefully mostly over Wednesday and Thursday, we'll be covering Chapter 19. And then maybe on Friday we might have a little finish, but then we might be able to do a little bit of review or practice or something like that on Friday as well. All right, any questions? All right, I forgot my little thumb drive today after I made up our clicker question, so we don't have one today. I know, that's such a sad thing. So what we're going to do today, we're going to look at a couple more examples of synthesizing polysubstituted benzenes. And then we're going to look at a couple of new reactions. And then we'll have a couple more examples at the end. All right? So let's think about, we've gone over, activating and deactivating effects and directing effects. We know that we have either ortho-para directors if they are activating groups, or we have meta-directors, which are deactivating groups, except for the halogens, which are deactivating and ortho-para directing. So they're the unusual ones. So let's look at these examples and think about or try to predict where a third substituent would go. All right, based upon the directing of the two groups that are already present. All right, so if we look at this first one, what about the ketone? What kind of directing does that have? That is a meta-director, right? Because it has a delta plus. Oops, what's going on here? A delta plus right here. Okay, so that's a meta-director, and the methyl group is ortho-para, right? So the meta-director is directing towards this position or this position. Right, the methyl group is directing towards the ortho or the para, but the para is blocked already. Right, so both of these groups are directing to the same position. Right, so they're complementary to each other in this molecule, and so the bromine then should go to one of the positions that is ortho to the methyl, meta to the ketone. All right? Straightforward. All right, what about the next one? We have the methoxy group. That is ortho-para directing. We have the methyl group like above, which is ortho-para directing. All right, so let's see whether they're going to be complementary or whether they're going to be conflicting. So the methoxy group is directing towards its ortho positions. Of course, in this molecule, the two ortho positions are not equivalent anymore. All right, so it's going toward ortho and para. Methyl group is directing towards ortho and para, right? So they are complementary, but they're pointing to three different positions on the ring. Okay, so we're going to likely get a mixture here, though there's one of the three possibilities which is more disfavored than the other two. All right, any idea which one that would be? The one on the top, right? The one that's right between two substituents. There's going to be more steric strain for it to go there than either of the other positions because it's ortho to two substituents rather than just one. Okay, so what we're going to say is that that one would be not formed, though it might be formed in some small amount. But we're going to say that the products that are favored are going to be the other two. So what kind of group are we putting on here anyway? A nitro, right? So we should have a product with a nitro group here. Plus a product with a nitro group here. And we're going to say that this position is disfavored. Okay, because of steric strain. Okay? Yeah, question?
So for the proportions of product form, would it be like a 1-to-1 ratio, or would one of these products be favored?
Yeah, good question. I don't think, I guess I would think that there's no reason to expect them to be exactly 1-to-1. But I don't think we have the ability to really predict it that much. If we just went based upon sterics, which group do you think would act bigger, the methyl or the methoxy group? Methoxy? See, I would maybe think the other way, because the methyl group, which is going to add the sterics, is actually one bond further away from the ring. Right? So there's the oxygen, which doesn't really, it has non-bonding pairs on it, but no actual atoms, and then the methyl is one further away. So I would say that maybe the methoxy would have a less of a steric effect. But I think it's hard for us to predict it here, so we're just going to say both of them are going to be formed. All right, what about the next one? Okay, so we already talked about the methyl group several times. Oops. So that goes ortho and para, but the para position is blocked. What about the amine? Ortho, para as well. Para position is blocked. So these two groups are... Is that doing it up there too? Keeps refocusing on me. Are directing towards different groups. Different positions, I mean. All right, so in this case, it's just going to be that the strongest activating group wins out. All right, so which is a stronger activating group? The amine, the NH2. Okay, so the amine is stronger activating. Okay, and so the major product is going to be ortho to the amine. What do you notice about the reagents in this reaction? Right, there's no catalyst, right? So remember, if we want to add a single halogen, a single bromine with a strong activating group like an amine, we don't need to put the catalyst, all right? If we had the catalyst in there, what would we get? Right, we'd probably get bromines at both of these ortho positions. Okay? All right, what about the last one? Okay, we have two different alkyl groups, right? So both of them are ortho-para directing, so it's going to direct here and here, or here and here. So it's kind of like the one above that, but now both are alkyl groups. all right? So do you think that one of those positions is going to be more favored than the other? So would it be favored either ortho to the methyl or ortho to the isopropyl? Ortho to the methyl, right? Because this isopropyl group is bigger and it's going to cause steric strain, so it's going to push it away from that position. Right, so these are two competing, but because there's more steric strain from the isopropyl group, the favored or the major product would be ortho to the methyl. Okay, so this is going to create some steric strain. Okay? At two other possible reactions here. Okay? So, I'm going to draw this, I'm just going to draw the product for this first reaction. Notice we have this halogen on there and a nitro group, and we're using hydroxide. We're reacting it with a hydroxide, followed by hydrochloric acid. Okay, so the product of this reaction is going to be this. Okay, so what's happening? It's a substitution, right? We've seen substitution reactions before. So what's different about this substitution? Right, it's substituting for one of the groups on there, right? Substituting for the chloride rather than substituting just for an H. Right? All the other times we had these electrophilic aromatic substitution reactions, but it was always an H that was replaced. Okay? So this is a substitution. Okay, what about the reagent? So always before we were reacting the benzene ring with an electrophile. Right? What about hydroxide? Is this an electrophile? Is it? No, it's not a good electrophile, right? It has a minus charge. It has a full octet of electrons on it. There's nowhere where it can accept electrons. All right? So it's not an electrophile. How does it usually behave as? Either a base or a nucleophile, right? So this is not an electrophile. Right? So this is not an electrophilic substitution reaction. So this would be a nucleophilic. Now let me rewrite that. A nucleophilic aromatic substitution. All right, so we reverse the roles in this case. All right, let's look at the second example here. So we're reacting with this sodium amide and liquid ammonia. And the product we're going to get, okay, is kind of like the previous one. Except we're going to substitute that for an NH2. But that's not the only product that gets formed. The other product in this case is this one. So that's weird, huh? Why would it go over there? Is this an electrophile? Is this here? Is that? Okay, so if we have sodium, so remember that this is sodium plus, and NH2 minus. The nitrogen has 2 non-bonding pairs of electrons. Okay, so what is the normal properties of this? Sometimes we draw this just as NH2 minus. Sometimes you see a sodium drawn in there. You could have a potassium in there. Remember, the sodium or potassium plus is just a counter ion. So it's just balancing the charge. It doesn't really participate. Right? So this acts as what? NH2 minus. Usually it acts as a strong base. Right? And in fact, this is the base that you probably use to remove the proton on a terminal alkyne to form an acetylide anion. Right? So it's a really strong base, and groups that are strong bases can also act as strong nucleophiles. All right, but something weird is going on because we're not just getting a direct substitution of this bromide, but we're getting some of our product. The bromide's gone, but we have some of the amine at this other position. Okay? So, what is this telling us in both cases? Are these similar to the reactions that we've already looked at? Are they following the same process, electrophilic substitution process? No, these have to be following different mechanisms. All right? And in fact, both of these reactions must be following different mechanisms, right? Because we don't get a mixture on the top one, we only get a mixture on the bottom. Okay, let me show you a little. All right, so I've just repeated the top reaction at the top here, but I've added one more example. And this example has now 3 nitro groups, and I got this from the old text, but I don't know having hydroxide at pH 7, right? That's neutral pH, and we know that at neutral pH all we have is the kind of the self-ionization of water, which means we have a tiny amount of hydroxide. But the point is here that we have a lower pH, so it's not as basic. And what about the temperature? It's a more mild temperature as well. All right? So what does it look like that these nitro groups are doing here? Right? We've learned already to categorize nitro groups as what? Right? We said that they were strong deactivating groups, right? But in this case, is it acting as a deactivating group? No, because the more nitro groups we put on there, the easier the reaction is. Okay? So in this case, for some reason, these NO2 groups are acting like, this is kind of redundant here, it seems like, activating groups. Dang, that deserves 2 exclamation marks. All right? So what does this tell us? Do we have what about the intermediate, right? In the electrophilic addition reactions, we had a carbocation intermediate, right? That was stabilized by electron donating groups, but destabilized by having an electron withdrawing group. So in this case, nitro groups are acting to speed the reaction up. So what does that mean about the intermediate for this reaction? Yeah. Right, so we got a switch in the intermediate, right? So electron withdrawing groups, what kind of intermediates do those stabilize? Anions, okay? We stabilize cations by donating electrons. We stabilize anions by pulling electron density away. Okay? So this means that the intermediate must be an anion. We'll just give that one exclamation mark. All right, so let's see, where am I going to fit this in? Okay, let's draw this out. For that reaction up above, the mechanism. Okay, so we have hydroxide, and we've said already that hydroxide is a better nucleophile. Okay, so the first step is going to be the nucleophilic attack of hydroxide onto the ring. All right, and it is going to attack at the same position as the chloride. So it's going to go like this, right here, and these electrons have to go onto the adjacent carbon. All right, so if we can fit this in, we're going to get an intermediate that looks like this now. It has the OH, and the chloride on the same carbon. We have an anion, we have our nitro group, and then we have two of these double bonds left over. Okay? Now, is this anion, is it going to be stabilized by resonance? Well, we have essentially an atom, this carbon atom right here. Right, come on. The carbon atom right here has non-bonding electrons, and it's next to a pi bond. Right? Is that a situation where we can have resonance? Yes. All right, so we can have resonance here where this non-bonding electrons, or these electrons, move down, and it bumps the electrons over to the next position. Okay, so this is the kind of resonance we can have with anions. Okay, OH. Now we have this, and oops, I can barely fit it in here, but we have the NO2 group and our non-bonding electrons right next to that NO2 group. All right, so what do you think? Having the NO2, the nitro group, on the same carbon where the anion is that going to help stabilize that anion? Yes, because in fact, those electrons can move out onto the nitro group. Let's just draw, here, let me redraw that nitro group, even though it's kind of crowded in here, so we can, it's easier to see this if we draw out the Lewis structure of our nitro group. So this is a plus right there. Okay, so there can be additional resonance here. We take this pair of electrons, make a double bond to the nitrogen, and then the electrons in that nitrogen-oxygen bond go out onto the oxygen. And so this gives us yet another resonance contributor. Like that. Okay? So by putting this nitro group, it's going to stabilize the anion. So it's essentially acting, a nitro group is acting as an activating group because we have a nucleophilic reaction with an anion as the intermediate. Okay, so how do we get to the product then? We have to lose, what do we have to lose? The chlorine, right? So let's just go from the first intermediate I showed. I'm going to draw the arrows to get to the product in green here. So it's going to be these electrons are going to go down here to reform the double bond, and chloride is going to act as a leaving group. Okay? And so if it does that, it will go straight to that product. Okay, so why are they adding hydrochloric acid in here as a second step? No, it's not so much about a lone pair. Yeah, it's a little bit ahead. We're going to actually talk about this more in the next chapter. But it's just acid-base chemistry, right? So the phenol has a pKa of around 10, probably even lower with that nitro group there. And so if we have it in a solution with a pH 14, that once that OH goes on, the phenol is going to become deprotonated. So it's going to be its conjugate base. And so we'll just have this equilibrium between the conjugate base and the acid. And so then we just add some acid in the end, neutralizes the whole solution, protonates the oxygen, and we just get the neutral product. It's what we call quench. Have you heard that term before? Okay, so we're kind of quenching or neutralizing the reaction is all it's doing. Okay? All right, so if we went down to the bottom one, if we drew all that out, this kind of added resonance right here could be drawn out for each of these nitro groups, right? Because our nucleophile would come in, we'd move our minus charge to the adjacent position, right? You could have resonance on this nitro group. We could then push those electrons down and bump them over to the next position, next to the nitro group, so it would have resonance there. We could bump it over one more. It would land where that nitro group is. It could have resonance out on that nitro group. So we're adding 3 additional resonance structures. Okay? So does it matter where those nitro groups are? If we have up there the nitro group being para to the chloride, right? Is it going to be just as good if we move that nitro group to the ortho position? Or roughly as good? Can we have the same resonance if we have the nitro group ortho? Yes, right? Because that's what we just talked about here. What about if we have the nitro group in the meta position? Okay, so if we were going to do the reaction, come on. With the nitro group at this position, would that be just as good? No, it wouldn't, because we would end up with the non-bonding electrons being, it would be like one of the examples we saw before that, say the minus would go over here, then it would go over here, right, 2 carbons over, then it would go 2 carbons past, and it would never land on the carbon where the nitro group is being attached, right? So it would have no added resonance. Okay, so this one would be not as good. All right, so we want to be able to understand why this nitro group can have a different effect for the electrophilic aromatic substitution reaction versus this nucleophilic aromatic substitution reaction. Okay? All right, so let's look at that reaction where we got a mixture of products. All right, and, oh no, these are more examples of what we were just looking at. Okay, so this one up here, we notice got the nitro group ortho to the leaving group. It's one I was just hand waving about and not writing anything down. And so this would put the methoxy group here. Right, so we're just doing a direct substitution. Okay, instead of using OH, instead of using hydroxide, we're using methoxide. All right, the bottom one, we have 2 nitro groups. We're using this amine. And so our product would again be substituted for the bromine, and we would end up with the secondary amine up here. So our byproduct now would be HBr. Okay, so the clue that tells us that we're going to do a nucleophilic substitution reaction is we have to see these strong electron withdrawing groups, particularly nitro groups on the ring, and that molecule is going to be reacting with a nucleophile, not an electrophile. Okay, so that's going to be... Okay, so now let's look at this last reaction where we saw a mixture of products. Okay, so what we saw was that we formed a mixture of kind of the direct substitution product and the amine being at the adjacent position. Like this. All right, so I think what this suggests, if we get the amine at both of those positions, is we have to have some type of intermediate that bridges reactivity of those two positions. Right? And so this one is really kind of surprising. I'm going to just do a little thing to make it easier here. I'm just going to draw, I should have thought about this when I drew the slide. I'm just going to draw the other resonance contributor, just so I can not draw so many arrows in our mechanism. Okay, so here's the bromine. And I can draw an H here. Okay, so the first thing that's going to happen in this reaction is that we're going to take this NH2 minus and it's going to act as base. So we actually start with an acid-base reaction. So this is going to pull off this proton that's adjacent to the bromine. And I'm going to just show the conjugate base of this. Okay, and so this is going to have a non-bonding pair of electrons here. And that proton is not really very acidic, so we need this strong base to be able to do it. Okay, now the even more surprising reaction here, I think, step, is that these electrons are going to essentially do an elimination reaction right here and push the bromide off. And so what's our intermediate going to look like? What do our arrows tell us? We're going to have a triple bond there. Okay, this is referred to as a benzyne. All right? Kind of weird, huh? This triple bond. We probably learned before that triple bonds could really only link into reaction rings like 8 or something bigger. But we can get this a very reactive intermediate. And then what happens is that our base reacts with this, and I'm going to run out of space. I'm going to take up space for what I've got at the bottom down here. So this NH2, okay, let's show how to get to the first product. This is going to come and react here, push these electrons over. Oh, I guess I'm going for the second one first. Gives us NH2, H3, and a minus. Let's see, what else am I doing here? Oh, I gotta have a double bond there. Like this. And then what do we have to do last to get to our product? Yeah?
Got a question on the triple bond. Why can't
Well, yeah, okay, so the bond angles that we talked about, right, SP 180, SP2 trigonal planar, SP3 tetrahedral, those are the desired, kind of the desired optimal bond angles, all right? Doesn't mean that they have to be that, but if you bend those bond angles away from the optimal bond angles, it just increases the energy. All right? So if you have something that wants to be straight and you bend it, right, it's going to increase the energy and it's going to want to snap back. Right? So it just takes more energy and it tells us that this intermediate is going to be very high energy intermediate. Okay? It's not very favorable. Yeah, question?
Does benzyne still have resonance? Or is it...
Good question. So what we'd have to do is think about how those orbitals are lying, right? So let's think about those orbitals for that benzyne. So I'm going to kind of draw this molecule from the side. Doesn't really have to be that one, but we know that, well, let's kind of do it there. So here's our CH3 over here. Right? We know that all of these other carbons have their p orbitals, and this is what delocalizes the electrons, right? And so these two positions still have those p orbitals, right? But what about so that just so far makes up a double bond, right? We got a sigma bond between the carbons, and now we've added one pi bond. So where does the other pi bond go? Right, it has to be in the same plane of the ring. And so our second, I'll just do these these are going to be kind of pretty much like p orbitals now. Would be like this. So the second pi bond has to actually be in the plane of the ring. Okay? So what do you think about your question? Yeah, it should still have resonance, so it still should be aromatic because we haven't interrupted the pi system that makes this benzene aromatic. We just added this new pi bond, which is perpendicular to the pi system, right? But I don't think that those can be purely p orbitals, right? The hybridization is probably slightly different. Okay, so the last step we have to do is we have to do another acid-base step. We have to protonate that position. Okay, and that proton is going to come from ammonia. All right, so this is just going to pull off a proton here. We form some more NH2 minus, which was our base in the beginning, and we get that product. All right, and we've added that proton right there. All right, the other alternative is, and I don't know how to fit this in here, is that this NH2 reacts at the other end of the triple bond. I'll do this one in green, so arrows. So it means that this would come into this position, and those electrons would go over to the adjacent position. Okay, so that would give us an intermediate that looks like CH3 here. We now have the NH2 here and the anion at this position. Okay? And then we just have one more step, is just to protonate that position. Right? So this is going to kind of go through here up to there by having, sorry this is turning out, I should have just put one reaction on this slide. Do you think? This is going to come and get protonated just like that. Okay? So this bottom one would function just the same. We don't have to try to fit it in here, right? So Na2 minus would pull off a proton that's ortho to the leaving group, form an anion, that would do an elimination to kick off the bromide to form the benzyne, right? And then our nucleophile, NH2 minus, could either come in at the same position where the leaving group was, or at the adjacent position, right? So we get two different products for that one as well. Okay? Weird, huh? Yeah, question?
Wouldn't it be favored not by the glow?
Well, yeah, so good question. So the question was, wouldn't it be disfavored next to the isopropyl group? And it would, but in fact, that the benzyne is only going to form between the carbon where the leaving group was and the adjacent carbon, right? So it only can go to these two positions. It won't go over next to that isopropyl anyway. Okay? There's just it's not scrambling all the way around. There's just two possible positions for that group to go. All right? Okay, so that's all of the reactions end of the chapter, but I did add a couple of extra synthesis problems on here just for fun. Yeah, all right. The more practice we get, the better we're gonna be. All right, so both of these, the aim would be to make them from benzene. Okay? So think about this for a moment and see if you can figure out a way to put that nitro group and that isobutyl group on there. Okay, so this first one, right, we have the nitro group on there, which is a meta-director. We have the alkyl group, which is orthopara. So what's the order, what's the sequence that we do here? Can we just put the nitro group on and then do a Friedel-Crafts alkylation? Can't do it. Yeah, because remember that the Friedel-Crafts reactions are the least reactive reactions that we have. And remember that they don't work if we have strong electron withdrawing deactivating groups on there. All right, so we can't do the obvious way, so we have to reverse it. Okay? So let's just put that as a note down here. Cannot do Friedel-Crafts alkylation with the nitro group on there. Okay, so that means that we have to make the other group, or we have to put on the other group as a meta-director. So we can then put on the nitro group and then convert that group to this alkyl group. All right? So we have to put that alkyl group on as an acyl group. Right? So the acyl group is a meta-director. We can do the nitration, and then we reduce the ketone to the alkyl group. So if we work backwards here, our next intermediate would have the acyl group on here. Okay, now we have two meta-directors. Right, and then we go back just to the having only the acyl group. Dang, my iPad keeps telling me that I'm having a memory overload. What about you guys? Are you having a memory overload? All right, so there's got to be our sequence, right? So the first step is going to be a Friedel-Crafts acylation reaction, right? So we're just going to have to use this. The next slide. Okay, somewhere there's got to be an oxygen. Pretend it's on that double bond. And then AlCl3 is our catalyst. Right, so we do the acylation, then we do the nitration, HNO3 and H2SO4. And then we can do the reduction. All right, so we can either do that Clemenson that I wrote yesterday, which is the hydrazine, the NH2 with base, or the other one is the, no, that was the Wolff-Kishner. The Clemenson one is, who wants to remember these names anyway? This is the zinc amalgam one. Remember my story about that? And this is done with HCl. All right. Okay, so I have this one other example. There's another example here. Let me just move over to it. So if you want to just write these down first off, and I will, when I get back to my office this afternoon, I'll record a little part of this to go on and show you how I would do these, and you can check up with it later. But then. All right, let's take a look at this next problem. Sorry we didn't get to it in class, but this will give you something more to practice. So the first thing is always to look at the substituents around the benzene ring and figure out their directing abilities and their activating or deactivating abilities. So we know that the nitro group is meta-directing, and it's a deactivating group, a strong deactivating group. The bromine is ortho-para-director, though it's a weak deactivating group, and the ethyl group is also ortho-para-directing, but it's an activating group. All right, so the most obvious approach here would be to put the nitro group on first, followed by either the bromine or the ethyl group, right? Because we could put one of those groups on because the nitro group is a meta-director. Problem is that we can't put that ethyl group on. We can't do a Friedel-Crafts reaction when the nitro group is on there. Okay, so we can't use that approach. So, like the problem up above, the approach has got to be to use the alkyl group as the source of the meta-directing group, which is going to put everything else in the correct positions. Alright, so if we go backwards to an acyl group here, we can see that if we would put the acyl group on first, then put the nitro group on, then both of these groups would be favoring meta-substitution, and we could put the bromine on last. Okay, so we're going to go from here. We're going to go back to this intermediate. Then we want to make sure that the next one that we take off here is the nitro group, because remember, we can't do the acylation either with the nitro group already on there. So we can go to here, and then that gets us back to benzene. Okay, so let's see if we can do this in the forward direction. Sorry. If we do the acylation, Cl, so this is acetyl chloride and aluminum trichloride. Okay, that's the Friedel-Crafts acylation reaction. Then we can do the nitration reaction. HNO3 with the sulfuric acid is the catalyst. Okay, puts the nitro group on. Now we have the two meta-directing groups, which will only direct to the position where we want the bromine. So then we can use bromine and iron bromide. Puts the bromine on, and now we need to reduce this ketone, but we don't want to reduce the nitro group. So the two ways that we have looked at reducing those will work just fine. Either one of those. The Clemenson, remember that's zinc amalgam and hydrochloric acid, or the Wolff-Kishner, which was hydrazine. Oops, let's see. Which was hydrazine and hydroxide. All right, so we have to consider, we have to keep in mind this limitation of the Friedel-Crafts reactions to make sure we don't try to do one of those reactions after we have a nitro group attached. Myself enough room in there, and okay. All right, so have a good 3-day weekend. Come back all rested and recovered. I'm sure you don't have a lot of studying to do right now. All right, the last example we have here has only a single substituent, but it has some side chain chemistry that we would need to do, right? So we need to end up with this aldehyde. So we have several ways we can do this. So let's think about what can we make an aldehyde from, all right? One thing we can make the aldehyde from is a alkyne. Remember, we can do this with a hydroboration oxidation reaction because we want the alcohol. So remember, this would go through an enol like this out on the end, which would tautomerize to the aldehyde. And so oftentimes we show things like this. It's a borane, right? Well, I've got two R groups over there. Just makes it bulky, controls the regioselectivity. Second step is basic hydrogen peroxide. Okay, so we'd have to get to the alkyne. Another potential functional group we could make that from would be an alcohol, right? And we can make the aldehyde from that by an oxidation with PCC. All right, so the question is, how can we make one of these compounds? The alkyne, we can't put it directly on the ring, but we could make that from a double bond in 2 steps. Remember, we could brominate it, right? It would put a dibromide on there, and then we could treat it with NH2 minus 2 times, and it will do a double elimination to form the alkyne. Right? We can make this alkene from this benzylic bromide. That we can make from the ethyl group, and that we can make from benzene. let's write it out in the forward direction. So the first step would be a Friedel-Crafts alkylation. So we could just use chloroethane and aluminum trichloride. Second step is a benzylic bromination. So we either use NBS and heat or light, or bromine and light. So that goes at the benzylic position. Then we do an elimination. We'll just use a bulky base to minimize the amount of substitution. And then we can brominate, double elimination to make the alkyne, and then the hydroboration oxidation. All right, so what about this other possible intermediate over here on the left? How could we make that compound? Well, one possibility would be that we could just convert this alkene over here, this is called styrene up here, to that alcohol using a hydroboration oxidation reaction. Right? And then we do the PCC oxidation to form the aldehyde. Now there is one more way to make that intermediate, but I'm not sure if you guys covered this last semester or not. So if you didn't, then just ignore it at this point. We're going to talk about this reagent coming up, though. So another way to do this is to go back to a benzene derivative that makes the benzene into a nucleophile. And so it's an organometallic compound like this. This is called a Grignard reagent. Okay, and the way that this works essentially is because magnesium is more electropositive than carbon. The magnesium gets a delta plus, putting a delta minus back on the carbon. So it makes this act like a nucleophile, like there's a minus charge there. So if we treat this Grignard reagent with an epoxide, then the nucleophile here can react and open up the epoxide ring. After it's done that, we protonate it, and then we get the primary alcohol. The Grignard reagent, in turn, we make from bromobenzene. Okay, all we have to do is mix this with magnesium metal. And then, of course, the bromobenzene we just make from benzene by a bromination reaction. Okay, so there's a number of different ways to come up with this side chain, and I particularly like problems like this where there's multiple ways. In fact, sometimes I'm surprised that students come up with synthetic approaches that are different than what I had even had in mind in the first place. Alright, so I hope this helps. I will see you guys next Wednesday.